open the floor to questions in a minute. Just these are some of my favorites. So number 23 was fun because it doesn't require much work at all. And at first you might say, how in the world? Well, let me show you how in the world. Is if you use that trig identity that tangent squared plus 1 is equal to secant squared, you can change this to secant squared x minus 1. And now we're pretty much done, aren't we? So if you didn't notice that, then yeah, of course this looks impossible. You're like, well, do we do sines and cosines? What do we do? But this, of course, we all know that the antiderivative of secant squared is tangent, and the antiderivative of 1 is x. Put a plus c in there, be happy, put a box around it. So that's it. If you floundered around doing something else, it's not that you're wrong. You could do this using sines and cosines. You might be able to do something else with this, but this is really it just does itself almost. Okay, so the other one that I thought was kind of cute was number 15. So let's take a look at this one, mainly because we didn't talk about cotangents. There are a couple of ways to deal with this. One way is to convert that cosine to 1 over secant. Oh, no, that's not going to help, is it? We could do that and convert the cotangent to 1 over tangent. But I think probably the easiest thing is to just take the identity that cotangent is cosine over sine and do that. So this is going to be cosine of x over sine of x times cosine squared of x dx. Now you have one of two choices. I'll do the easier one, but either one works, just so you know. One way you could do this is to separate out a single sign. You might say, how do you do that? Well, stick a sign here next to this dx and change this sign to sine squared. That's one option, and it will work. It's more complicated, though, than what I'm going to do. What I'm going to do is I'm going to take this extra cosine, and I'm going to move it over. Let me show you what I mean by this. This will become cosine squared x over sine of x. So I'll just combine those two. And then I've got my cosine over here. Now, whenever you group, at least the way that I think of this, and hopefully you're starting to think of this way, is whenever you group something along with your dx, that's going to dictate what your substitution is. And so my substitution is going to be that u is equal to sine of x, and du is cosine of x dx. So you can kind of see where this is heading. We're going to turn this into du, and we'll put a u down here, but we still have to deal with the cosine squared, but that's not hard. So let's just do a little bit of rearranging, and then I'll finish this one up. So this is equal to 1 minus sine squared, because cosine squared is 1 minus sine squared, and then I've got just sine down there, and then here's the cosine of x dx. So let me just pause, because this is a little bit more involved than number 20, whatever it was, the one with tangent squared. So is any questions? Anyone lost their minds? I don't know if you wanted to admit that. So if you have lost your mind, come see me tomorrow. I've got plenty of time. I'm happy to sit down with you and find your mind. Okay, so if we're happy with this far, now the rest of this, it almost works itself out because we end up with something that we're familiar with. So let's make that substitution. This becomes 1 minus u squared over u du. And here, this is something that you did in Calc 1. Let me remind you how you do it, though. So back in Calc 1, you had problems like this, and the first time you encountered them, you said impossible. But then you learned that what you could do is you could do a little bit of algebra, just a little bit, it's not a lot, and you could separate this into two fractions, in particular 1 over u minus u squared over u. And so now that's easy to do. I'll just write it one more time. So this is the natural log of u minus u squared over 2 plus c, of course. And now we can go back to our, what is it, sine? Yeah, u equals sine. So this will be the natural log of the absolute value of sine minus sine squared over 2 plus some constant of integration. Whoops, sorry. Now that I'm looking at this, I need to warn you about something. I don't know if anyone here used some sort of online integration tool, Desmos, or what are the other ones? I don't even know. But if you used one of those, you might get an answer that is correct, but looks very different from what I have here. And the reason for that is because of all of those identities that we've been using. For example, this is the same as this. Let's see, sine of x plus cosine squared of x over 2 plus some constant. I'll call it constant 1. So I've had this happen to me when I've been checking my work. I'll sometimes get my answer, and then I go and look online, and I'll be like, oh, wait, that's minus, this is plus. It's not too hard to get from here to here. The only thing to note is that the constants are different. Like if you take this and you use some identities to get this, you'll have this minus 1/2, I believe, plus that constant. And so the constants all get lumped together, and so that's why that happens. Also, this natural log of sine is the negative of the natural log of the cosecant. So you have some relationships there that just there's these weird things that you might see. Ooh, let me do one. Do I want to do this? I don't know. Let's see if there are questions first. And then there's another one that is kind of fun that's not on your list. Ryan, you had something? 25. Go right to the end. So this one, yeah, so I looked through and I picked the ones that were fun for me. Number 25, I put in the category of tedious. So it's just tedious. It's not very fun, but I'll get you started. I really prefer not to do the whole thing. So let me get it started. Then I'll see, Ryan, if you had a question about some particular thing. But so 25, yeah, I try to avoid tedium, but sometimes it's unavoidable. Tangent to the 4th times secant to the 6th. It's that secant to the 6th that makes this so tedious. Okay, so let's just explain, first of all, the thought process that I would go through when I look at something like this. First thing I ask myself is there an even number of secants? Because if there's an even number of secants, I can move 2 of them over, turn the rest of them into tangents, and call it a day. That's the case here. The other question, if that's not the case, then I'll ask myself, are there an odd number of tangents? Because if there are an odd number of tangents, I can separate out one of them along with one of the secants, and then turn the rest of the tangents into secants. So anyway, that's sort of the thinking that I go through. And then if neither of those are true, then I crawl up into the corner in a fetal position. No, that's not entirely true, but yeah, it's not as fun. There's other things to do, but okay, so this one, there's an even number of secants. And so what I'm going to do is I'll separate 2 of them. So let me just do the first 2 steps, and then Ryan, I'll see if you have specific questions beyond that. So here's the secant to the 4th, and then you have a secant squared dx. And of course, the reason, hopefully you recognize why I'm doing this, but just in case, let me just make it super clear. The reason is that I'm going to be doing this. du is secant squared dx. In other words, u is equal to the tangent of x. So you can see there that I've separated out those 2 secants in service of this particular substitution. Let me just do one more step, and then we'll get back to your questions. So the other step is to note that secant to the 4th is secant squared squared. And so I'll use that identity. Specifically, secant squared is tangent squared plus 1. And then we have that secant squared x dx. There. So let me pause for just a sec. I'll do one more step, but I don't want to do this one fully because, like I said, tedious. But Ryan, does that sort of get you over a hump, or is there an additional question? Okay, so that's, yeah, so it's sort of like sorting out. And at this point, now you're like, okay, now we do the substitution, and it becomes this ugly thing. And I'll show you. So this is going to be u to the 4th times u squared plus 1 squared du. So you can see where everything ended up down here. There's still, so the tedium is, I'm going to have to expand this. I've got to write this trinomial. I've got to get it all, before I do the integral, I've got to deal with the algebra. And algebra, just tedious. It's necessary, but tedious. All right, so there it is. Anything else from this that we need to look at? Yeah, what do you think, Christopher? 11? I didn't even notice that one. Oh, 11. Yes, 11. Okay, let's deal with 11 together. 11. This is the one I made a mistake yesterday. So I'll tell you my mistake, and then I will make up for the mistake by doing this one. My mistake was, and this is a change, usually when I teach this section, I write down the following identities. Let's see, first of all, sine squared of x is equal to 1 minus the cosine of 2x over 2, and cosine squared x is 1 plus the cosine of 2x over 2. So we have those two identities. I usually write those down and I say use those, but I didn't, and because I thought, why do we need this? We can just do the integrals. Remember, I had the integrals instead of having the identities. And I got to be honest, at the very end of class yesterday, I realized my mistake. So now I do penance by doing this problem for you. So let me do this. So I'll use those identities. So if you use these two identities, that's the key to this. So let's see what this looks like. I'm going to leave off the limits just so I don't have to write them over and over again. We can put them in at the end. So I have sine squared, cosine squared. Oh, you know what? There is an additional identity. This one I did have. Sine of 2x is 2 sine x cosine x. So you remember, this one I did have yesterday. Okay, so now that I'm looking at this again, here are your two options. Two options, I think I'm going to choose to use the one that's boxed up there. Two options are, number one, use this. I'll show you how. Number two, use these two and then suffer. Let's do this one, though. It's a little less suffering. So let's do that first one. So you'll notice sine of 2x is 2 sine x cosine x. And so what I'm going to need to do is I'm going to need to rewrite this. And here's how I'm going to do it. I'm going to write this like this. I have, okay, I'll do it in stages. Sine of x, cosine of x, quantity squared. So hopefully that doesn't bother you. Now I'm going to employ that double angle formula for sine. It's not exactly correct. Notice that I have 2 sine x cosine x up there, and down here it's just sine x cosine x, but that's easily corrected. Just divide both sides of this identity by 2, and you'll get what's down here. So this is sort of the key here, is that I could do this. So this will become 2, no, not 2, sorry. Sine of 2x over 2 quantity squared. And just see, can I get it all up there? I'll zoom back out in a sec, but see if that makes sense. That's the first step. Yeah, this one's rough. Yeah, like I said, right at the end of class, I realized my error in not sharing those identities. Okay, let's finish this up. It's not too bad from here. So I'll just move this over a bit. So this will be sine, let's see, the integral of sine squared 2x over 4. And now you might say, well, wait a minute, I don't know how to do that. Well, you could either use the formula that I had last time for the integral of sine squared of x, which is totally fine. Or you can use the identity up here that says that sine squared of x is equal to, hold on a minute, I'm going to put 1/4 here just to make it. So sine squared is, here, I'll zoom out and then I'll zoom back in. It's going to be 1 minus the cosine of 2 times x over 2. Now you notice I've left a big blank there because up here I have sine squared of x equals this. Down here I have sine squared of 2x. And so I need to make an adjustment and say that that's going to be 2 times 2x. We're almost done, believe it or not. So the last bit is to simplify just a bit, and then we'll do the integral. So this will be 1/8, if you don't mind me pulling that 2 out, of 1 minus the cosine of 4x dx. If you need to, please do use substitution there. I don't need to because I know that the antiderivative of cosine is sine, and because of this 4x, I end up dividing by 4. It's just that we've done this so many times that I feel like we don't really need to write down all the substitution. I would encourage you, though, to always double check your work. What I mean by that is when you get done writing this, before doing anything else, just think in your head, what is the derivative of this? Derivative of x is 1, good. Derivative of 1/4 sine of 4x, cosine of 4x times 4. Oh yeah, it does work out because the 4's cancel. So, don't just write it down and say it's always going to be 1/4. No. Do it, but then double check. Now let's put our limits. Finally, the limits are 0 to pi over 2, 0 to pi over 2. And so that equals 1/8 times pi over 2 minus 0 minus 0 minus 0. The sine of pi over 2 times 4, pi over 2 times 4 is 2 pi. The sine of 2 pi is 0. And then when you plug 0 into this, you get 0. I would encourage you to always write the lower limit, even if you think it's 0, when you're dealing with sines, cosines, natural logs, just because weird exponentials, weird things happen. Okay, so my final answer, which I hope is the right answer, is pi over 16. I don't have my back of the book because I just have the portion of the book for this chapter. Oops, there it is. So hopefully it's right. But does that help out for everyone who's joyously doing this? Okay, so I think that must be it. Let's move on. We got to do a quiz. Just a sec. Let's see. Is this one going to be hard? I hope not. I tried to make it obvious. So let me just say this. Yeah, you don't need any weird identities. Here, I'll even write down the only identity that you should need. You could choose, let me just explain though, you could choose to use other identities, but the only one that you absolutely have to use to do this is this one. Sine squared, the one that everyone knows, plus cosine squared x is equal to 1. And you're, of course, going to rearrange that a little bit, but give it a go. We'll see how well you do, and then we'll see if we have time for even more trigonometric joy. There we go. Here we are. There. 1, 2, 3. Sorry about this. 1, 2, 3. 1, 2, 3. Let's try. Here we are. 1, 2, 3. Let's see, I think there's 2 there. I hope there's 4 there. So we're going to find out. I think I printed exactly 26, so everyone's here. Does anyone have any extras in the back? Okay, perfect. We're good. No one's watching from home, but if they were, there's the quiz. So. Hmm. Oh. Oh, I should put that. Sorry, I put that identity back up there. I think everyone knows this, but there it is. Yeah. So like I said, you could choose to use other identities and still get these problems right, but this is the only one that is essential. So if you're trying to use other identities, maybe you should back off, I guess. I don't know. realized I stole this chair the other day. We'll put it back after. I sense some of you are ready to go. If you're still working, don't fret. You know, it takes a little bit of effort, but if you are done and you want to just pass it over so I can get a feel for how many we have and how many we're waiting on, that's fine. Is that Michael? Yeah. Oh, thank you. Yeah. No hurry. Thanks. I can come get this. Still recovering. You're bad again? Oh no. Are you the one that gave the sickness to Dr. O? No. Okay. Thank you. All set. Ah, nice. Well, some of you are still savoring the experience, but we do need to move on in a bit. So if you're still working on these, maybe you could at least put down the substitution that you would be using. So just like, here's what U is, here's what DU. So make sure that that's there so that I can say, oh yeah, you know what's going on, even if there might be something that is hanging up getting the final answer. So that to me is the most important, is making sure you've got a substitution that will work. All said. Oh, I know. You're just meditating on me. It's fine. I'll come back around. He likes to look at it for as long as possible. Yeah, I don't want to rush you. When you had the test on Friday, were you the last person here? Were you? Okay, so you stared. Okay, no, it's fine. Yeah, I know. Yeah, it's good. It's good. No, you're usually right. Oh, good. More here. Let's see. Just peek. Don't want to make you nervous. I just want to see how far you are. Yeah, just doing the final thing. You're doing great. Yeah, give it a go. Yeah, so I'll come back for it. But you're there. Yeah, just go ahead and finish that line. You have your substitutions. All right, very good. Yeah, so just actually do that substitution here. And then, you know, as long as you have that substitution, you know where it's going to go because it's just a polynomial. All right, have you meditated long enough?
Yes, thank you.
If only I can't see with it. Yeah, oh yeah, okay, yeah, very nice. Very good. All right, I'll come get yours in just a sec. Got something now? You're happy? Excellent. Well, I'm pretty happy actually, so good job. All right. Yeah, this is the important stuff. So you've got the important stuff written down, so that's good. So, yeah, so maybe I could take what you have, and if you want, we can talk about how to maybe strategize on getting this in. So thank you. All right, so I think I've got them all now. Anyone else holding out on me? Okay, let's go ahead and take a look at what I have. I hope I got it right. I didn't check my work against your work, but we shall see. Here's the first one. I mentioned that identity was the only one that you should need for both of these. That didn't work. I'll deal with this later. So the key here is there's an odd number of signs, so you're going to separate one of them out so that you can do this. So I had that negative that I threw in there, and I need these signs to turn into cosines. And then once you do this substitution, you have this nice expression, which is a polynomial, easy polynomial. So the answer there is just this. So I don't know that there's any other variation to this that would be, work. I think that's the only way to do this. The second one, there were two ways to do it, and a couple of you chose to do it the hard way. Oh, wait, you got a question? No, I refuse to lose a minus. I love spreading the negativity. And so just notice that if you take, you're talking about the one out here, this one? Yeah, so if you spread that negativity, you get -1 times u squared, which is negative u squared. And then negative times negative u squared times u squared, you get positive u to the fourth. Yeah, so I guess I'd skipped a step. So you can, if you wanted to, you could multiply this first. You get u squared minus u to the fourth, and then when you negate it, u to the fourth minus u squared. It's common. So if you had the backwards, it just meant that yours got lost somewhere. It's a good question though, because I often lose my negatives, even though I'm a pessimist. And so I try my best to keep the negativity around. Okay, well, let's go look at the second one. So this is the way I did this. The other way works just as well. It doesn't look as good. So if you just do this very straightforward substitution, u is equal to tangent, which means du is secant squared, and you're pretty much done because there's not much to do here. No trigonometry, whatever identities, and there's my answer. So if you did it the other way, by the other way I mean if you let u equal secant and du was tangent secant, yours is going to look very different down here, but it is the same function. You'd have a bunch of secants. I think, two different fractions. So there it is. Okay, one last thing before we move on to the new stuff, and I don't know how much of this new stuff we're going to get through, but is this one. So this is just a fascinating thing, and I need to mention something about this. So this integral, if I gave you this integral and said do this, I'm guessing that very few of you would get a final answer just by if this was on the quiz, because you've never seen how to do this. And when mathematicians work these things out, they have no idea. Like the first time, I don't even know, I can't tell you who historically was the first one to figure out this particular antiderivative, but someone did, and that person probably was just tried things. They tried doing one identity, and then they tried another identity, and then they mixed things up and moved things around, and eventually they got the answer. The easiest way to do this, I think you probably could do this by changing this to 1 over cosine and doing some tricks with the various identities. But one easy way to do this, and this is going to look like magic, but it is not, is to do this. To add or not add, multiply this secant by a fraction. Now, let me just point something out. When mathematicians do this, we know that if you put the same thing on the top and bottom of this fraction, you're going to get 1, and that's legal from an algebraic standpoint. So that's in fact what happens here. It's not a that I multiply this by, it's secant plus tangent, secant plus tangent. And bear in mind, like when you read a textbook, when you read a math paper, you're not seeing all of the failures. This is the way math is done. You get a failure, then another one, and another one, and you're going over here, getting failure after failure after failure. Eventually, you find a success. So it took you a whole lot of math to get to that success. But when you publish the paper, all you see is problem, success. None of those failures. And so you have no idea, how did someone come up with this? I don't know. They must have tried a whole bunch of stuff, but this is like I said, feels almost like magic. Let me show you that what happens. So I have this secant x squared plus tangent secant over secant x plus tangent. Okay, now the good stuff. Let's let u equal secant plus tangent. du. What's the derivative of secant? It's secant tangent. And what's the derivative of tangent? It's secant squared. Amazing. Isn't it magical? That is du. Anyway, so there's that. And so this ends up equaling this, 1 over u du, which is just the natural log. And so the antiderivative, I'll just write it up. Yeah, there it is. Oh, well. I'll write it down here. It's going to be the natural log of the absolute value of secant plus tangent. Plus c, of course. So this is the antiderivative of secant. By the way, you can do something similar, actually easier, with tangent. And when you do that, you get the natural log of the secant. So these basic trig functions, they have antiderivatives. It's just, they're there. So, so when you see this, you're like, where did it come from? Well, someone did the work in the background. Okay, we do need to move on. I don't know how far we're going to get, but we're going to find out. So we're doing trigonometric substitution. Why? Why would we do this to ourselves? Here's why we would do it to ourselves. It's because we have various integrals like this that don't have trig integrals, don't have trig functions in them, but they are functions that we could turn into trig functions. And once again, you might be thinking that you're going out of the frying pan and into the fire when you do this. And in a sense you are, but we do have the tools to solve trigonometric functions, trigonometric integrals. And so if we can take these and somehow modify them to turn them into trig integrals, that's what we're going to do. So I don't know if you wrote those down. You don't have to. Here's the one that we're going to work on first. Sorry, I should have ignored. I just wanted to show you, like, there's a whole bunch of integrals like this that you might say, can't I use regular substitution? Well, yeah, there's a problem with that, though, is like there's nothing to, there's no good substitutions for these. Like, these are just ugly. But using trig substitution, you can do these. So here's an example. Now, to understand trig substitution, what you need to understand is that what we're doing is we are substituting with trig functions. And so we need to know what trig functions we're going to substitute for. Trig functions, of course, are related to triangles, right triangles, in fact. And so here is theta. And so let's just write down what is the sine and cosine of this angle. So if you had to tell me what is the relationship between that triangle and the sine and cosine, what would you say? So I'm sure most of you have some clue, but if you don't, that's okay. We'll help you through it. Americo, do you have any idea about either sine or cosine? Do you remember from your trig or pre-calculus days? You might have had a little mnemonic. I know you're the first one. Yeah, SOHCAHTOA. Yeah, SOHCAHTOA. So sine was opposite over hypotenuse. So maybe you remember this. If you don't, well, maybe it's jogging here. I'll write it up here. SOHCAHTOA. Sounds like a chant of some sort. Yeah, here, the opposite and adjacent and hypotenuse. Yeah, that's one way to do this. This is great. So sine is opposite over adjacent. Cosine is adjacent over hypotenuse. Tangent opposite over, sorry, I think I got the sign wrong, right? Sine is opposite over hypotenuse. Tangent is opposite over adjacent. There. Whew, I just have to remember my SOHCAHTOA. So here's how this relates to this. You're still probably thinking that has nothing to do with this picture. Here, I will make it look, here, I'll show you. let's just get rid of the 3. Whoops, I got rid of too much of that. Give me a sec. Put that line back in. Now, let's suppose that instead of doing having this look like this, let's suppose that I just put an x over here. So far, so good. I can call that x, can't I? And I could call this 3. You're like, what? Where did that come from? Well, you'll see in just a minute why I chose 3. Now, we all know the Pythagorean theorem. The Pythagorean theorem says that x squared plus this, we'll call that b for now, plus b squared is going to equal 9. That means that b is the square root of 9 minus x squared. You see where this is going? I hope so. It's so, I mean, I don't know. For me, it's fun. I realize that for you, it's torture. But, whoops, I appreciate you. Whoops, keep erasing. I shouldn't have erased that now that I think of it. Let me put it back in here. I appreciate you letting me have a little bit of fun. So here. Okay, so let me put this in here, 9 minus x squared. Now let's actually just finish this up. The sign is x over 3. That's opposite over hypotenuse. The cosine is the square root of 9 minus x squared over 3. Yeah, that's right. That's the adjacent over hypotenuse. Yeah, isn't that fun? Okay. And then finally, we're going to need to figure out this dx business, but you can see this is the substitution. Essentially, we've done most of the substitution that we need. Let me just rewrite both of these. So here, this is x is equal to 3 sine of theta. So notice that all I did was I took the x over 3, multiplied both sides by 3. Same thing goes down here, just to make things easier to digest. This is radical 9 minus x squared is equal to 3 cosine. I still need a dx, but I think that we can do this. I think some of you might know. Let me pick a volunteer, Michael G. If this is x, what do you think dx is? Yeah, it's the derivative, right? 3 cosine. So this is x, so the derivative of x is the derivative of this, which is 3 cosine. 3 cosine of theta d theta. Amazing. Now that we have that, let's go and plug that all in. So that's all the work. This is the work that you do on the scrap paper. Now let's go crank this over here. It's almost miraculous. It's amazing. So this becomes the, let's see, 3 cosine of theta. Okay, so here, I'll highlight just so that you see what I've done. This became this because of this. Okay, let's do the bottom. On the bottom, x squared becomes 9 sine squared. And here we go again, that this becomes this because of this. Is that all visible? So far, so good. I guess the x squared got a little obliterated. So we see all the connections so far. And now the dx, it's a straightforward connection there, I hope. That last one, I won't highlight it because I'm running out of colors. That will be 3 cosine of theta. So good. Okay, so that is really the most important part of what we're doing this week with this trig substitution. So let me pause and make sure no one's completely lost, because this, I mean, there's some beauty, I think. This gets me super excited. So if you're excited, you can join the club. It's hard. I don't want to say that it's not hard. It's hard, but it's still kind of cool. Okay, let's finish this one off, and then we'll take a look at a second one. Okay, so let's see, I'm going to simplify this a little bit. And because I'm on PowerPoint, I can't scroll. So I'm going to do this I'm going to combine two steps, but I'll speak them and then I'll write them. Notice 3 times 3 is 9. 9 over 9 is 1. So the 9's cancel. Second, I have cosine times cosine, cosine squared, over sine squared. Cosine over sine is cotangent, and so this will be cotangent squared. Now, before I go on, I just want to point out that this is not the only way to do this one from here on out. I think, well, probably there's other ways to get to here, but I think that this is the way that all of us, if we were to set this up using trig substitution, we'd all get to this point, the point with all these highlighting. Here is where we might diverge. And as we found with the homework for today, there are a lot of ways, well, maybe not a lot, but there are usually multiple ways to go about this. So I'm going to just show you the way that I want to go about it. And, you know, if it differs from you, that's fine. That's fine. So you might have been discouraged. Well, actually, no, I'll just go for it. Okay, so here's how I'm going to go about this. You know how we have sine squared plus cosine squared is equal to 1. So you know about that one. If you divide everything by cosine, this turns into, or cosine squared, this turns into tangent squared theta plus 1 equals secant squared theta. And then if instead of dividing everything by cosine squared, if you divided them all by sine squared, you would have 1 plus cotangent squared is equal to cosecant squared. 1 over sine is cosecant. That's the one I'm going to use. In particular, cotangent squared is cosecant squared minus 1. Okay, so you still might be wondering, how is this going to help? But bear with me, trust me on this. So this thing becomes the integral of cosecant squared, theta minus 1. I'm pretty sure all of us can handle this 1 here. It's the cosecant squared that you're going to have trouble with. So let me just remind you from your Calc 1 course that some of you may remember this, some of you might not, that this is equal to negative cotangent. In particular, the derivative of cotangent is the negative cosecant squared. So that's what we're using here. And I regret not change. Well, I think I may need to change over to Notability soon because I am almost out of space. So this whole thing is equal to the negative of cotangent minus theta. Sorry, the theta looks bad, but there it is, theta. Plus c. Yeah, I'm sick of this. I'm going to switch over. Give me a sec. I have to take a screenshot. I put the screenshot over into Notability, and then I am happy. Copy and delete. There it is. Okay, it's far better. Okay, so almost done. We're getting close. So the last bit is to say I've got things in terms of theta, cotangent of theta minus theta plus c. So I have things in terms of theta, but my original problem had x in it. So what I'm going to need to do is I'm going to have to ask myself, what is the cotangent? Well, tangent is opposite over adjacent. Cotangent is the reverse, adjacent over opposite. So that's easy enough. Well, sort of. Adjacent, 9 minus x squared over opposite. There's cotangent. Now you might say, well, what in the world do we do with theta? Well, theta, you have several options, but the easiest option is to use this. X is equal to 3 sine of theta, which means that x over 3 is the sine of theta, which means that the arc sine of x over 3 is equal to theta. Now, of course, this will restrict the values of x to some degree because the domain of arc sine is between -1 and +1. So you'll have some restrictions on your solution here, but nonetheless, oh yeah, so if this thing can never be bigger than 1 or less than -1, it means that x has to be between -3 and 3. But if you accept those restrictions, this will serve as theta, arc sine of x over 3. And that is my answer. Amazing, amazing. I love this section, this chapter 7, and I realize I know that you don't love it. It's okay. It's okay. You know, just let me have my joy. Okay, let's see. We've got 5 minutes. We can start one more, and then we will postpone. Well, I'll tell you what to do for the homework. So the homework, oh, we need to talk about homework as well, because I think I'm ready to resume my job fully. So I'll tell you about that in just a minute. But for now, let's talk about this next example just a sec, just to get it started. Let's see, which one did we do? We just did this. I don't want to do this. I don't want to do that. Don't want to do that. Why don't I want to? I want to do this. Okay, here. Just to get us started, to show you, yeah, okay, let me just mention why I just skipped a bunch of them. Because every single one of those would have looked very similar to this. There's some rearrangements, but it would look almost the same in terms of the substitution. So those are all very similar. This one, though, is different. So let me get started on this just to show you what I mean. So with each of these trig substitutions, the first step, at least when I do them, if you look at the book, there are other ways to go about this, but I find this to be the most understandable. So the first thing I always do is I draw a triangle, I put theta in there, and then I start thinking about this radical. So the radical, that's the key to this problem. Back here, the radical was 9 minus x squared, and I did this without telling you I was going to do it. Some of you saw, like by the time I said Pythagorean theorem, you're like, I see where this is coming from. So I was clever. I chose to make this 3 and this x so that that would be that radical. Whenever you have a minus, that's the way this is sort of going to shake out. But if there's a plus, it's not going to be quite so straight. Well, it is sort of straightforward. So in this case, what you're going to want to do is if I put an x here and a 2 here, now if you do the Pythagorean theorem, you find that this side is that radical, x squared plus 4. Because this squared plus this squared equals this squared, right? X squared plus 2 squared is equal to what's under the radical there. And we're all done. Now, if we do this, then instead of using sine and cosine, you're going to be using tangent and secant. So this will be the last thing we do today. Write down what you think the tangent, of theta, the tangent is, and write down what you think the secant of theta is. Just take a minute, do that, and then I'll talk homework. And I'll pick some randos. I know I've been bad about this today. I'll get some. Darren, do you have any ideas for tangent for this problem? Yeah, x over 2, which means x is 2 times tangent. But we'll do that on Friday. All right, Ben P. Do you have any idea about secant? Now, let me just remind you, secant is the reciprocal of cosine. Oh, here, I'll even give you, I know this is the hard one, so thank you for being willing. So sorry, ca. So let's do cosine. Oops, do cosine for me.
2 over the radical.
Yeah, 2 over the radical. So if secant is the reciprocal of cosine, then the secant is the radical over 2. It's, I don't know. I keep saying it feels magical, but every time I do this, it feels magical. This is going to be down here. Tangent is going to be down here. We'll be able to do a similar trick that we did with the last one to figure out dx. Okay, so what should you be doing? Like I said, I think I've recovered fully, and I think that by Monday, I'll be able to start doing the, actually recording our, I've got my stamps here. I'm really excited. So we'll go back to actually checking that you're doing your homework. For Friday, though, we don't have it. I've got the homework online. I'll adjust. But I think you'll be able to do at least the first problem on the homework and probably the fourth problem. So when you look at the homework, I think it's 1, 2, 3, and then I've got 3 additional problems. So I think the very first one, and I think the whatever is fourth on the list, you should be able to do. You don't have to hand it in on Friday, but it would be nice if you actually tried at least one of these to see how it goes. And then we'll see how things go. So we'll finish this on Friday, and then, like I said, next Monday, we will resume collecting homework or putting stamps or whatever. Just, it's been a couple of weeks here where I've appreciated you giving me a little bit of grace. All right, I'm going to stop the recording if you want to come chat.